All right, so today we're going to finish up our discussion on normal distributions. So last couple days we've been talking about when we have a normal distribution, how do we take a value and convert that into a percentage, an area under the curve? So what percent of values fall within a given range? Or yesterday we talked about if I want a certain percent, so if I want the top 10% or if I want to find the 20th percentile, how do I convert that percentage back to a value in the context of the problem? So today, what we're going to talk about is when we're given a distribution, how do we determine if it's normally distributed? So given a distribution now, instead of being told it's normally distributed, we have to determine that for ourselves. Okay, so we're going to talk about a couple different processes we can use to determine or assess normality to kind of finish up this discussion with these normal distributions here. So when we try to assess normality, okay, there's three different pieces to this process. So typically, we might want to start with a graph of the distribution. So when I create the graph, if I notice any obvious skew, so skew to the right, skew to the left, we can stop right there and say we definitely are not approximately normal because our normal distributions have to be symmetric. So that's a way to eliminate a distribution. But if I plot the data, so I make a histogram or make a dot plot, and I see that it's approximately symmetric, that doesn't necessarily define a normal distribution. So we talked about the fact that all normal distributions are symmetric, but not every symmetric distribution is normal. So as far as making the graph is concerned, it's a way to eliminate normal distributions. So if I see it's skewed to the right or it's skewed to the left, I can stop there and say we're not approximately normal. But if I do make a graph, if I do make a histogram, and I see that it is roughly symmetric, then I would have to go to one of the other two pieces that we see there to actually determine if it is in fact normally distributed. So we said if it is normally distributed, it has to follow that empirical rule. So it has to follow that 68, 95, 99, 7 rule. So what I would do is I would check my intervals. If I make an interval that's 1 standard deviation above and below the mean, I'm going to check to see if 68% of my values fall within that interval. And then if I go 2 standard deviations in each direction, do I capture 95% and so on? So if I see that it follows that empirical rule fairly closely, then I can determine that it is approximately normal. The other option is what we're going to use the calculators for, and that's to check what we call a normal probability plot, or you can abbreviate that as an NPP. So by looking at a normal probability plot, we can determine if a distribution is in fact normal or not. So what we're going to do is we're just going to go through a couple examples. So the first thing we're going to do, we are given a set of data. So below are the data on the unemployment rates for the 50 U.S. states. So what I want you guys to do is I want you to take a minute here. I want you to put those values into your list 1. So if you're given the data, first thing you're going to need to do is you're going to need to put this into your lists. Oh, what'd you do? Okay, so as you finish up, just kind of double check, just scan through real quick, typed everything in correctly, make sure you have the 50 values. Now on a problem like this, so we have the data, in this case the 50 states, the unemployment rates. I wouldn't necessarily do this first step. We're going to show you what it looks like, just checking the graph, right? I wouldn't necessarily do this in this particular instance, okay, because it just takes more time than is really necessary for a problem like this. But if I wanted to, I could take this data and I could make a graph. So in this case, I could create a histogram, or I could create a dot plot or a stem plot, whatever you choose to do there. And again, the graph is useful for eliminating normal distributions. Like if I see an obvious skew to the right or skew to the left, I can stop immediately and say we're definitely not approximately normal. But in a situation like this, where it's roughly symmetric, there's no obvious skew one direction or another, I see that it's symmetric, so it's a possibility that it's normally distributed, but that doesn't guarantee that it is. So this is just something where if they give you the graph, you can use it to try to eliminate the normal distribution. It doesn't necessarily prove that we're normal just by looking at it. So what would happen then is we would want to use one of those other two methods for determining normality. So we would either use that 68, 95, 99, 7 rule, or we would use that normal probability plot. So for the empirical rule, once you have the data entered, you would run your 1var stats. So everybody go ahead and run your 1var stats real quick just to verify that you get the same numbers that I have up here. So stat over to calculate, 1var stats. You should get a mean of 8.682, and you should get a standard deviation of 2.225. So because we established that the graph is roughly symmetric, we move on to this next step. We actually check the 68, 95, 99, 7 rule. So what's going to happen is I'm going to create 3 different intervals. Now, at any point along the way, if I'm way off from a normal distribution, I can stop and make my conclusion at any given time. So the first thing I do is I make my 1 standard deviation interval. So I take the 8.628, I add 2.225, that gives me my upper bound. I take the 8.682 and I subtract the 2.225, that gives me my lower bound. Now as I look at this interval, so 6.457 to 10.907, I would go back to those individual values. So I'd go back to my data set and I would count how many values are in between those two numbers. Okay? So I would use this table and I'd count how many numbers fell within that interval that I created. So when I do that, in this particular instance, I get 36 out of the 50 total states fell within this first interval. So that gives me a value of approximately 72%. So as we're looking at this, like we said, in that first interval, I should capture somewhere around 68%. So in this case, we happen to capture 72%, so we're a little bit off. Okay, but we could check the other intervals just to see if we kind of get back on track. And so when I check my second interval, okay, I go 2 standard deviations above and below, so I can either go back to my mean and add 2 times the standard deviation and subtract 2 times the standard deviation, or I can just use that first interval, add the 2.225 to the top, subtract the 2.225 from the bottom. I get my new interval, and then I count how many observations fall within that interval. And so in this instance, we would get 48 out of the 50 states, which gives me 96%, so that's pretty close to the 95. And then I check that last interval where I go 3 standard deviations in each direction. And when I create that interval, it captures 50 out of the 50 or 100%, which is right around the 99.7. So the graph told us we were roughly symmetric. When I create my 3 intervals, I more or less follow that 68, 95, 99.7 rule. So based on that information, we would be able to say that this is in fact approximately normal. Okay. Now this particular method can sometimes, depending on the problem, be a little bit tricky because there is a little bit of subjectivity. That first interval captured 72%. That's not right at the 68 like we would like to see. It's a little bit far away, but I would say if you're within around 4 percentage points of that first interval, you're probably still okay to proceed. But again, someone else might look at that and say 72% is too much, so this is not approximately normal. So this particular method opens itself up to that subjectivity. Sometimes you might say one thing, someone else looks at it and says another thing, so it can be a little bit tricky here. So this is one method we can use. It's one that when you're on the homework, when you check the answer key, I have this all worked out. So you have the intervals, you have how many values, what the different percentage breakdown is, okay? But in my opinion, this next method that we're going to discuss is probably the better one for a situation like this. So when they actually give you all the data points, we're going to create a normal probability plot. And so for a normal probability plot, what's nice about this one is I don't even care what the original graph looks like. When I check this normal probability plot, I'm either going to have my approximately normal distribution or not, and it's going to be very obvious. Okay? So on your calculators, if I want to create a normal probability plot, the first thing you would do is put all the data into your calculator. We already did that. So once I have everything in list 1, I'm going to graph the data. So I'm going to go to second y equals so we go to second y equals, that's that stat plot. So anytime I say go to your stat plot, that's what you're going to. You're going to choose plot number 1, and just like we do with the lists, we're always going to put everything into list 1 just to keep things consistent. Whenever we go to graph our data, we're always going to choose plot number 1, and we'll change whatever we need to in there. So you choose plot number 1. First thing you want to do is turn it on. So make sure to hit enter on the on part. And then when you go to select what type of graph you want, so if you go down 1, there's 6 different graph options. We want the very last option, so you're going to scroll all the way to the right and hit enter to select it. And then once you've selected that last graph option, just double check that the list they're asking for or looking for is the list you put your data into. So it should be list 1 for most of you. So second y equals, get into that stat plot, choose plot number 1, turn it on, go to the last graph option, make sure it says list 1 or whichever list you put the data into. Once you're ready to graph then, and this is going to be pretty much consistent throughout the different types of graphs we create, once I have everything set up the way I want it, you're going to hit the zoom key in the top middle. And then you're going to hit the number 9. So after you hit zoom 9, you should get a graph that looks very similar to what you see up on the board there. Keep scrolling right. There you go. Okay, so everybody should be looking at that same screen there. So when we look at the normal probability plot, what we're looking for, what they're doing is they're graphing the z-scores. So the calculator's calculating all the standardized values, and it's graphing them. If it's normally distributed, those standardized values should line up fairly well. So I should see a fairly linear pattern. So in this instance, when I look from start to finish, I can see that for the most part, the data lines up pretty well. Now, even though there are some ups and downs, right? So there's a little bit of curve here and there. We're not worried about little curves within. We're looking from start to finish. Does it appear to be fairly linear? So if I make my normal probability plot, I would sketch this on my homework. So like if you do this on the homework, you would sketch a graph, like sketch what you see on your calculator, and then draw your conclusion. Since the MPP is fairly linear, this distribution is approximately normal. Or the MPP is not linear, so we are not approximately normal. So this one, I think, is one of the better options for assessing normality because it's a little bit quicker in most instances, and it's a lot less subjective. Okay? If I see a nonlinear pattern, okay, it's going to be fairly obvious when I look at an MPP that's nonlinear. I'm going to have from start to finish either a curve this direction, skewed right, or a curve this direction, skewed left. And if I see anything like that, then I know I'm not approximately normal. Okay? So when we're checking these, that 68, 95, 99, 7 rule is always an option. Create the 3 intervals, count how many values fall within the interval, and then convert it to a percentage. If it follows the 68, the 95, and the 99.7, we're good. If it doesn't, then we're not approximately normal. If I check the normal probability plot, I just provide a sketch of what my calculator shows me. If it's fairly linear, we're good to go. If it's not linear, then that means it's skewed one direction or another, in which case it's not normally distributed. Okay? So then another example here real quick. So on this problem, they give us a dot plot and they give us the summary statistics for data on the calories per serving in 77 brands of breakfast cereal. We want to know if the distribution is approximately normal. So since they gave us a graph, we can check it real quick. If I see any obvious skew in one direction or another, we'd say we're not approximately normal, be done with the problem. Now, if I look at this dot plot, though, do I see any obvious skew? No, it's fairly symmetric, right? So the graph doesn't eliminate the normal distribution, but it also can't prove it either. Symmetric doesn't necessarily mean normal. So then the next thing, I have the summary statistics. So when I check those summary statistics, I can use those, the mean and standard deviation in particular, and I can create my 3 intervals. So when I create my 3 intervals, so I reach 1 standard deviation in each direction, 2 standard deviations in each direction, 3 standard deviations in each direction, what I notice is that in that first interval, I capture almost 82% of my values. So at that point right there, that's nowhere close to my 68. That means we're not approximately normally distributed. When I look at the second interval even, we're below that 95% quite a ways. Like the more I go, the closer I should get to the true values. So I should be really close to 95 and I should be really close to 99.7. But in this case, those first 2 intervals are quite a bit different than what we expect. So in this case, even though it was roughly symmetric, we're not approximately normal because it does not follow that normal distribution. The other thing you could do, if you're given something like this, okay, so we have the actual data here. If they didn't give me the graph, if they didn't give me the data and they just gave me the summary statistics, what you can look at is how does the mean compare to like the quartiles? How does the mean compare to the min and the max? You can look for that symmetry there. If we're looking at a normal distribution, that minimum and that maximum should be about 3 standard deviations above and below the mean. So if I were to calculate the z-scores for my minimum and maximum, The minimum should be about -3 standard deviations. The maximum should be about +3 standard deviations. If I'm not around there, then I know I'm not normally distributed. Okay, so I can check that as well in terms of the overall distribution. So we can use any of those aspects we know about the normal distribution to check based on the information they give us. So if they give us the data, I would probably check that normal probability plot. If they give you like a graph and summary statistics, maybe check the intervals. Or again, you can check kind of how that min and max relate to that mean to make that determination as well. Last thing then, you're going to have a couple questions. Just going back to that z-score formula. So given information about a normal distribution, calculating the mean, calculating the standard deviation, basically using the z-score formula. If they give you 3 of the pieces, you need to be able to solve for any of the others. So in this particular instance, or this example here, it says according to a study by Rescue Time, people spend an average of 1.25 minutes on their smartphone each time they pick it up. So if Noel's distribution of smartphone use is approximately normal with a mean of 1.25 minutes, and it has a 97th percentile of 2 minutes, we want to calculate the standard deviation for this normal distribution. So as I look at the problem here, they give me the mean. Okay, so they give me the mean. They give me an x value. And then they give me a way to calculate my z-score, my standardized value, by giving me a percentile. This goes back to yesterday's conversation. So if this 2 minutes is the 97th percentile, we can calculate the standard or the standardized value for that. So when they give me that 97th percentile, I can take that percentage and I can convert it back to a z-score using that inverse norm function on the calculator. Or I can look up 0.9700 on table A, which will allow me to convert back to a z-score. And then that gives me the z-value, leaving only the standard deviation to be solved for. So I plug in the x, I plug in the mean, I plug in my z-score, and then basic algebra, we solve for standard deviation, and in this case, we end up with 0.399 minutes. Or they might give you a situation like this where they give you a percentile, the x value, they give you the standard deviation, and then you have to calculate the mean. So it's just a matter of using the equation, using the formula, and manipulating it for whatever piece you're looking for. Okay. So here are the problems I'd like you to try out for that then.